Okay, so we are talking, first of all, I know there's only one person watching this, but this video might get used for other years, but to that one person that's watching this, I hope you had a good holiday. Right, so we're talking about structures, right, as part of the mechanisms and structures unit. So there's a couple of things that you have to be informed about, right? So a structural engineer is interested in understanding how forces act on different structures, so that when they're designing them, they can try to make sure those structures don't move too much, okay? To try to take into account the forces that might act on them that might result in the failure of those structures, and to try to remove them. Now, in terms of forces, there are seven. Oh, what's happening there? There are seven forces. I'm using a wee graphics tablet, so it's all over the shop, right? So there are seven forces. Okay, there is tension. So that's where something gets stretched. There is compression. That's where something gets squashed. There is bending. There's twisting, we call that torsion. That's S-I-O-N. It's not going very well. There is shearing, so that's like cutting. Shear forces. Right, so these are actual forces. There's another two forces that we use, but these are kind of descriptive. Okay, static forces and dynamic forces. Now, static forces describe a system where forces are acting on something, but the thing isn't moving. Okay, and that's infinitely possible. So if you had a body and there are forces acting on it, when we represent forces, we represent them with little arrows. Yeah, we call them vectors. Okay, so you could have a system that was like that, one force going that way, and then another force acting on that body going that way, the same size. Yeah, so there's two forces acting on that body, but it's not moving. Okay, that's called a static system. Then you could have a dynamic system where you've got a body with forces acting on it, but the forces perhaps, or maybe there's another force, maybe there's a, oh no wait, it was here, maybe there's another force. You know, so there's a static system, there's a dynamic system, there's three forces acting on that, and that thing must be moving, okay, because the forces don't resolve easily. So we've got tension, compression, bending, torsion and shearing, and static and dynamic, right? Task one, little exercise that I want you to do, I want you to create, just to show your understanding, I want you to create little diagrams for these, little pictures. Create icons for the forces. Now I've already given you two. I've already given you static and dynamic. I just want to see if you understand them, right? So tension is when something's being stretched. Compression is when something is being squashed. Bending is when something's being bent. Torsion is when something is being twisted. Shearing is when something is being cut. So create icons for these forces, right? Just to show you your understanding. And we'll talk about them because, you know, when I see, if you draw me pictures, it'll inform me as to what you think about these forces. So I want you to draw little pictures that represent them the way I drew pictures down here for these two. So those are the seven forces, right? The next bit that we're going to move on to is, so you can pause the video now and do task one, do it in your Jota or do it electronically, I don't mind, right? And then pick the video up again. Okay, so moving on from that, we're going to do a little bit of maths. I'm going to introduce you to something, right? What we do is we look at complex systems and we simplify them. And when we simplify them, we create a thing called a free body diagram. Free body diagram, it ignores the effects of gravity, it ignores the effect of self-weight. It's as if the thing's floating in a vacuum, right? So if you've got, the classic one is if you've got a road bridge, obviously I'm sketching on here and it's not ideal, right? If you've got a road bridge that's supported on pillars, in the ground, yeah, and maybe there's like an arch structure underneath there, and then there's legs coming down that support the roadway, yeah. And this is the roadway on the top here where vehicles can go in there, and there's the road line up the middle. So that's, you could have a vehicle on here. I'm going to try to draw a lorry. There's an alright wee sketch. Yeah, this will do. There you go. And big wheels on there. Big wheels keep on turning. Group that, right, so you've got a lorry driving on that bridge, right? What we'll do is we'll create a free body diagram of that system where we'll simplify it for National 4 and 5. So we'll represent the roadway just with a flat line. We'd represent the lorry as a force acting down on the roadway. And then we'd represent the supporting structure as reaction forces. Chances are you're always going to have two supports, yeah, so we call that reaction 1, reaction 2, and a force. So we would see simplified structures, we'd see these vectors, these arrows indicating the forces, and we would also see distances on here, okay? A free body diagram includes forces and distances. Distance 1, and then you obviously need at least one more distance to fix that force in place. Okay, so that's a typical free body diagram, and we can start doing maths around these if we know what's going on. Okay, so what we're going to do is we're going to talk about what we call static equilibrium. Now this is something that structural engineers really care about. Static equilibrium. Now we know what static means. It means that the thing isn't moving. Equilibrium, it's just a fancy way of saying we know there's forces acting on it, but all those forces add up to 0, right? There are 3 conditions for a thing to be in static equilibrium. These are called the conditions for static equilibrium. 3 conditions, okay? The 3 conditions are that all the vertical forces should cancel each other out, all the horizontal forces should cancel each other out, and all of the twisty forces should cancel each other out. So here's how we do it, right? We use a mathematical symbol called sigma. What that means is sum of, it means add them all up, right? So what we're saying here is the vertical forces, vertical, the sum of all the vertical forces must equal 0. Don't get caught up about this symbol, just listen to the words, the sum of all vertical forces. Take all the vertical forces and add them up and it should equal 0. So in this instance here there are 3 vertical forces, 2 going up the way and 1 going down the way. If this bridge isn't moving, then that means that the force going down the way must be equalled by the 2 going up the way. They must add up to 0. There's another condition for static equilibrium, and that's that the sum of all the horizontal forces must equal 0. Yeah? In this system there aren't any horizontal forces, but it's the same deal. You understand, if there's leftward pointing forces, they must be balanced by the rightwards pointing forces so that the thing's not moving. And then the last one is the sum of moments. Now we'll come to moments again later, but that's about rotation, okay? So the sum of the moments must equal 0. So anything that's trying to make the thing rotate must equal 0. And there's a different way that you can write these. So that's my first take, but a more simplistic way would be to say the sum of all the upwards forces must equal the sum of all the downwards forces, yeah, and the sum of all the rightwards forces must equal the sum of all the leftwards forces. That's the horizontals. And then for the moments, the sum of all the clockwise moments must equal the sum of all the anti-clockwise moments. So that's just another way of saying the same thing. These are the three conditions for static equilibrium, right? And these are the things that we focus on when we're trying to work out any missing forces or any missing moments or even any missing distances, okay? So let's look at it at its most simple, where we just have a body with a force acting on it, and I'm going to give that a value. I'm going to say that that's 12 newtons, okay? So the units of force, you get this in the data book, the units of force newtons, capital N, right? So if we've got 12 newtons acting to the right, what would we have to add in order to make this thing static? We would have to add, we would have to add a 12 newtons to the left. Oh, goodness sake, that's annoying that went down the way, but you get the picture. 12 newtons. So now the condition is static. Things get a little bit more complicated if we try to do things at an angle. So at National 5 we do work with forces at an angle, but we work with them on squared paper, and we do scale drawings. Obviously we're going to find that difficult to do that remotely using computers. I'll see if I can figure out a way, but if I can't, I don't know, we may have to just do that whenever we're in person, right? But we can stick with some of the simpler stuff, or sorry, we can stick with the math based content, right? So let's see if we can work out some let's see if we can work out just a flat beam question, right? So if we've got a beam and there's a force acting, I wish I hadn't done that down anyway. There's a force acting down in the middle, and that force is 400 newtons, and the beam is being supported on two pillars, and one of those pillars is taking 300 newtons. What's the other pillar taking? So mathematically we could work this out as the sum of all the ups must equal the sum of all the downs. So the ups are 300 plus the unknown equals 400, and that's the only downwards one. I can rearrange that mathematical formula. I can move that 300 over the other side. So that would become question mark equals 400 minus 300 equals 100 newtons. Fantastic. So that's the simplest exercise we can do here. So let me set you up with some really simple questions there. Let's do a bunch of beams or three bodies. Use that slight angle, don't worry about it. 1, 2, 3, and let's put some forces on. Let's see if you can identify the missing ones. And I would like to see sketches. would like to see sketches on these, right? So and then up here, oh, every time. Get rid of this. Sorry about this, give me a wee second. Welcome to Remote Learning 101. Yep, and then we'll set this up. And we'll stick some numbers in. Right. So I'm going to do live questions. Right, so let's call that 620 newtons. Let's call that 410 newtons, and I want to see writing the maths out and getting used to using that kind of terminology. 9 kilonewtons. Let's see, that's 7.7 kilonewtons. Let's go for 4.6 kilonewtons and 5.2 kilonewtons. Let's see, that's 2 newtons, 5 newtons, 4 newtons. Obviously these wee ones down here will be easy, but they'll only be easy just now. R1, R2, R3. So you're working out R1, R2 and R3, and then you're doing a sketch to show me how these three need to be balanced. Okay, so you have 6 questions. 1, 2, 3, 4, 5, 6. Brilliant.